A coated aperture microscope for X-ray fluorescence full field imaging. There's a lot there to unpack. Let's get to it. The coated aperture part means this. We have gold, 25 microns of gold deposited on silicon nitride and then etched into a pattern. The pattern here happens to be an order 73 modified uniformly redundant array. What the heck is that? Well, it produces images that look like this. So A is the measured data that we get from a fluorescing X-ray source. The source in this case is a gold wire mesh with 25 micron wires on a 300 micron pitch. So we see the retrieved image by computational analysis of A at the right. The beam energy here is 20 kiloelectron volts, which corresponds to a wavelength of 62 picometers. So the resolved resolution here of around 15 microns is many orders of magnitude greater than the wavelength, but still it's an interesting image. Let's figure out how it was made. Computational imaging. Episode 21, Coated Aperture Imaging. Episode 20 considered divisibility as a model for creating imaging systems with geometric rays. And in particular, we focused on the pinhole camera as a way to do this imaging and had a very simple forward model with the pinhole creating the impulse response. The problem with that system, among several others, is that the light efficiency is very poor because only rays passing through the pinhole are imaged. We can improve the efficiency by drilling multiple pinholes, which leads us to coated aperture imaging. So we put a coated pattern on the aperture, we see projected images of the code from the object, and then we can try to computationally invert that to image the object. This is a step toward what might be the ultimate goal of not just having a system that works, that produces an image, but trying to come up with a system that has the optimal coding strategy. What visibility function optimally resolves the object? Today's discussion won't resolve that question, but will lead us to some interesting ideas for how to think about it. For the pinhole system, we derive the visibility by saying that the visibility is 1 if a ray passes through the pinhole and 0 if it's blocked by the screen. We use the circ function to turn the visibility into an impulse response, which was defined here in these projective coordinates. For the visibility function for a coated aperture, we just replace the circ function by the transmittance function of the coated aperture and use the same projections on the variables to evaluate that function for our impulse response. For the pinhole camera, that led to the forward model where we integrate the object against this circ function impulse response. For the coated aperture, we get the same forward model, but replacing the circ function by the transmittance of the coated aperture. Now, the coordinates and the projections here are a little bit cumbersome, so we can simplify things by working in projective coordinates. Instead of xy, we define theta x to be x over the range to the object and theta y to be y over the range to the object. To simplify things a little bit more, we'll assume that the range z is much greater than the thickness of the pinhole of the coated aperture camera, which will take out a few terms in our description and allow us to have this very simple two-dimensional transform between the object density integrated along the path z and the coated aperture. So we have basically a convolution between the coated aperture and these scaled projective coordinates against the object density. Okay, now this is our continuous forward model. We'd like to make a discrete forward model, of course. So let's assume that we're going to have our measurements on this output plane and that we have square pixels on the output plane that are going to integrate the data from the projection. So we have a pixel function, p, which describes this rect pixel, and we'll assume the pixels are evenly spaced with the pixel spacing delta. And then we can define the discrete values g sub ij to be the integral of the continuous projected field over the ij pixel. Now we could also make the code discrete. We could of course have a continuous code, but our math will get a little bit simple if we assume the code consists of cells, and the code spacing is delta sub t. Ultimately, we'll assume that the pixel spacing on the code is the same as the pixel spacing on the detector, just to make things a little bit simpler. But we have a transmittance function describing each cell, and then in each displaced value of the cell, we get a code value t sub l m, and the continuous code transmission function is the sum of the transmittance of the discrete coding elements. Substituting the discrete form of the transmittance function into the discrete form of the measurement, we get this expression where we have the code value t sub l m multiplying this integral, which depends only on l, m, I, and j, the parameter numbers for the code and the parameter numbers for the pixel, and we can summarize that as this f sub hat of I minus l and j minus m. F hat for particular values I and j is the integral of the f hat in continuous form in the projective coordinates against the discrete pixel at the ijth position. But this pixel is integrated against the code sampling function and the pixel sampling function, so it's this p hat, and then we evaluated at I minus l, which was l was again the sampling element on the code, and I would define the sampling position in the pixel space. This convolution of the code element and the rectangular pixels function has this triangular form shown down here. This forms a natural sampling function for the object space. And eventually we want to estimate the object on some natural or some basis that makes sense for the object, but this happens to be the natural sampling function that arises from this kind of geometry. With this sampling function and this discretization of the code, the overall forward model in this form. So now the forward model is just the convolution of the code pattern with the unknown object. Okay, we want to invert this, of course, to estimate the object. We could use any of the variety of inversion strategies we discussed in Chapter 3. But today we're going to talk about what if we made the code to be particularly easy to invert. In fact, we could say, what if we made a complementary code, this t-circ, that we're going to convolve with the measurements to recover our estimate of the object. So this isn't necessarily some kind of optimal strategy, but it's an interesting strategy that has been used, and it leads to some interesting discussions about what would make an optimal code. Now, the code turns out to be based on, or there's a variety of different codes, but the one we're going to talk about is based on this idea of a quadratic residue. An integer q is a quadratic residue modulo an integer p if there exists an integer x such that x squared is equal to q mod p. Complicated kind of statement. Let's choose a particular integer, in this case 17. So here is the integer 17. We're going to print the integers between 1 and 17, and then we'll square those integers. So the 1, 4, 9, 16, so on. And then we take the modulation of the mod of the squared value mod 17, and we see, for example, 1 squared mod 17 is 1, 2 squared mod 17 is 4, 3 is 9, 16, 8. So a variety of integers appear here, but not all integers between 1 and 17 appear. So some integers between 1 and 17 are quadratic residues, and some are not. And so we'll define a quadratic residue function to be 1 if the integer is a quadratic residue mod 17, and 0 if it's not. So 1 is a quadratic residue, 2 is, but 3 does not appear in this list of integers here, so 3 is not. Similarly, 5 does not appear in this list of quadratic residues. It turns out that these quadratic residues create a structure in the number line that has interesting properties. If we take a quadratic residue code, here for example we've created the quadratic residue on the base of 293, which happens to be prime, and convolve it with itself, it turns out to be sharply peaked. So the idea of a code that when convolved with itself produces a delta function is called a perfect sequence. These quadratic residue codes are not quite perfect sequences, but they turn out to be something close. The integer p doesn't have to be prime according to our definition, but if it's not prime, then the code will not have this same structure. Okay, so this is a basis for creating codes, and we won't get into all the details of coding theory here, but we will imagine that what if we could create a two-dimensional code for coded aperture imaging based on these quadratic residues, and not something that we imagined, but something Fenimore, Cannon, and Gottesman imagined back in the 1970s and came up with a proposal for what are called uniformly redundant arrays. So uniformly redundant means that they have the property that when convolved with themselves, they produce delta correlation. And so we'll define the forward code as shown at left here. This would be our choice of the coding elements of the coded aperture. So if along the value I equals 0, it's 1. If j equals 0, but I is not equal, or it's 1 if I equals 0, or 0 if I equals 0, 1 if j equals 0, but I is not equal to 0, and then 1 if I and j are quadratic residues modulo the base of the code, 1 if neither are quadratic residues, 0 otherwise. The complementary code has the same properties except a particular value I equals 0, j equals 0 is 0, and then it has a bipolar values as 1 and -1 values, whereas the transmission code only has unipolar values 0 and 1. On the base 73, here's what those codes look like. You see this little tiny thing up in the corner is 1. In this code, the yellow, this is a complementary code, yellow is 1 and dark is -1. On this code, dark is 0 and yellow is 1. Okay, so we've generated these codes, and here's where the magic happens. We take the codes from the previous slide, convolve them with themselves, and you see you get this very sharp delta function when the codes are exactly overlapping, and otherwise you get 0. So that means that if we have measured the convolution of the object with the forward code and we convolve with the conjugate code, we can recover a delta function impulse response which recovers the object. The code that's given in the GitHub generates these codes exactly according to the algorithm from Fenimore et al. So we go and we set all the code values equal to 0. Then we set the ones where j is equal to 0 equal to 1. And then we just go through all, we've made the quadratic residues we found all the quadratic residues for the basis p, and we just go through all of the I and j values, and if the quadratic residue state is the same for those two values, we set the code value equal to 1, and then we find the complementary code by setting the j equals 0, y equals 0 equal to 1, and the other ones equal to plus or minus 1 according to this form. And then the quadratic residues were generated for a given base p. We just go through all the values between 1 and p and check if they're quadratic residues. Some of the values might be a quadratic residue more than once, and of course some of the integers between 1 and p never get to be quadratic residues, and so they're not quadratic residues. So it's a very simple way for us to find the quadratic residues. We've got our codes. We've got our complementary codes. We're ready to take images, and then so we just have to convolve with the complementary code to get our image. Here's an example of doing that. So in this case, it's a order 59 Mura code. The Mura is the modified part of the uniformly redundant array. Goes back to, this was Fenimore and Cannon's second attempt to develop codes, but at this point we can just call them uniformly redundant arrays. But we get measured data like shown here. Now, the code has to be kind of circular, so actually you have to tile the input plane with the code, not just a single version of the code. So things are a little bit complicated, but we can see that we faithfully reconstruct the object by deconvolving the convolved data with the complementary code. If we add noise, the deconvolution still works, but we get a noisy reconstruction. Here's a simulation with Poisson noise added to the system. You see that there's noise in the measurements and noise in the reconstruction. The signal-to-noise ratio has scales like this. N is the number of non-zero transmission elements in the code. So for order 73 code, N is going to be somewhere between 100 and 1,000. So we get an n times increase in the amplitude of the signal. We also get a root n scale increase in the noise. Now the thing, if we have multiplex codes, a measurement gets noise from that particular signal value that we're evaluating, but also from the other signal values that are shifted on top of it. And then also we have the possibility of background noise. If the background noise was dominant, if we could ignore these other terms, then our signal-to-noise ratio would be increased by a factor of n by doing this kind of multiplexing. But in a Poisson-dominated system, the signal-to-noise ratio does not increase relative to a pinhole, absent analysis of the structure of the noise, which we'll talk about in just a second. Now, in contrast, for a focal imager, the noise for a given pixel depends only on the Poisson noise for that pixel plus background. So a Poisson system will tend to have a much better signal-to-noise ratio than this coded aperture system. But the coded aperture system could be the only game in town if you don't have the possibility of doing focal imaging. Now, as previously mentioned, there's simulations of this coded aperture imaging system on the GitHub repository. And so the simulations of, for example, reconstructing these minced hand-drawn digits with the measured data and the reconstructed image, again, assuming that the code is cyclic, which means we have to tile the coded aperture plane with the code. If we add Poisson noise, we get something like what's shown here. Now, this is all assuming we use a linear estimator, which of course we would almost never do. One thing we could do is take the estimated code from the deconvolved linear estimator and see if we can denoise it. First of all, our results depend on the noise level. The previous slide was assuming only 100 photons per measurement on average. Here we're assuming 1,000 photons per measurement, which gives us better signal to noise. But if we go in here and say, okay, well, we want to denoise this, we of course could build a neural network to do the denoising. So we're going to take our measured data or our reconstructed image after the deconvolution and try to denoise it using a neural estimator. So we take the 28 by 28 minced figure, feed it through this UNet. We're going down to just 7 by 7 images with 32 features in the middle of the UNet, and then reconstructing the image through the denoiser. If we do that, we get something like this. The top row is the ground truth images. The middle row is the estimate you get by deconvolution with the complementary code, and the bottom row is the denoised image. That looks pretty amazing. Will that always work? Well, let's try. What if the measurement, or if the object was a random array of pixels? So our measurement would look like this. Now there's not structure for the network to analyze and pick out what's noise and what's signal, so the reconstruction is not as effective. However, with this denoising, you see that the reconstructed signal estimate for the coded aperture system relative to the pinhole system is much better. The difference here comes about because for the pinhole system, the Poisson noise is correlated to the structure of the object, whereas for the coded aperture, it's not correlated. It's distributed over the whole plane, so it's easier for a neural system to come and find the noise and take it out. So this is a super interesting thing. We've built a forward model for a system. We had a pinhole. We said, well, can we do better than a pinhole? So we tried a coded aperture, and we look back, and there's this idea of some kind of ideal deconvolving coded apertures that have a particular simple coding structure. It's the start of a way for us to think about how to build forward models for geometric imaging system. In the next few lectures, we'll get more sophisticated and think about strategies to really understand how to make useful coded aperture systems for X-ray imaging. There are some conclusions to draw from what we've seen. Pinholes and coded apertures enable imaging when no optical elements are available. So if we can't use a lens, this is coding the visibility as a way for us to create a structure that allows us to image the remote object. The angular resolving power is equal to the size of the pinhole divided by the range to the sensor. If there's code, that A would be the size of the coding element. So the coded aperture doesn't increase the angular resolution, but does improve throughput. This compares to the angular resolution for a focal system, which would be, we'll find will be the wavelength divided by the aperture. If you take the ratio of these, the ratio turns out to go like the, for the optimal sized coding element, goes like the square root of the thickness of the object divided by the wavelength, so it's going to be something on the range of 100 to 1,000 times better for a focal system. Uniformly redundant arrays are very cool, very interesting kind of coding elements. It gets to the idea of could we make optimal codes, but they assume the object illumination is uniform. If we go to non-uniform illumination, we may find that quasi-random arrays are better. They also assume that the object is two-dimensional, which it's not. So we need this decoding structure of the uniformly redundant array doesn't work the same if the object is three-dimensional. They assume linear image estimation, which we actually never use anymore, so we may be able to find better codes. Then coded aperture systems increase SNR when the target is the dominant feature in the scene. If the target was weak with a strong background, pinhole imaging might actually be better. Noise that is not spatially correlated to the image can be removed with neural processing. So we've seen our first neural denoising system. Neural systems perform poorly if the object is not structured according to the training data, if it's just a random object uncorrelated to something. But they work well if they're finding features that are known to the system. Okay, next time we're going to go into 3 dimensions. Objects are 3-dimensional. Here we see a dancer, Cynthia. Back at my days at the University of Illinois, we had a camera array surrounding Cynthia, as you see in the picture at lower right. We talked about neural radiance fields a couple lectures ago and showed that we could generate new views. Here you see Cynthia's surrounded by a cloud of points. That's because this is a true tomographic 3D reconstruction. We've back projected rays to create a 3-dimensional image. So we'll talk about how to do that in our next lecture.